Good afternoon, everybody, and thanks for being here the last session of the last day of the conference. And of course, I wish to thank the scientific committee for giving me the opportunity of presenting some of our results, and also giving me the opportunity to visit the Toledo, which is a most still beautiful city despite the heat. So I will discuss some results we obtained in the photoelectron dynamics of atoms and molecules in the tender X-ray domain. All the work has been performed at Icpeac, same lab as Francis, so Laboratoire de Chimie Physique, Matière et Rayonnement in Paris. And all the results I will present have been obtained at Soleil, at synchrotron Soleil. So we do photoelectron spectroscopy of core levels of isolated atoms and molecules. So we look at electron and nuclide dynamics after core excitation and ionization. And in this particular field, most of the results have been obtained in the soft X-ray regime. Now, there isn't a definite barrier between soft and hard X-rays, but let's say soft X-rays up to 1 kiloelectronvolt. We work in what we call the tender X-ray regime, which is 1 to 15 kiloelectronvolts, and after that you have hard X-rays as high as you can go. Now, why up to now most of the results have been obtained in the soft X-ray, like core levels of the first elements? Because up to very recently, it wasn't really possible to have a close look of dynamics in the tender X-ray regime because of experimental limitations. But now we have a new beamline at Soleil, which is called Galaxies, with an end station for high kinetic energy photoelectrons. And then this beamline provides zero-DR performances in the tender X-ray regime. So now we are in the position of observing really subtle effects in the tender X-ray regime. So this is the scheme of Galaxy. It's an undulator double crystal monochromal beamline. It has two end stations, one for resonant inelastic X-ray scattering, and I will talk of results obtained with what we call the Icpeac, the hard X-ray photoelectron spectroscopy end station, which is equipped with electrostatic hemispheric analyzer. Can collect electrons with kinetic energy up to 12 keV with a very good resolution. And this end station, it's the result of a collaboration between the group of Marc Simon, Icpeac, and Soleil, and it's permanently installed on Galaxy. So I will discuss basically 3 examples of our work on galaxies. Doppler broadening in Auger spectra due to recoil by fast photoelectrons, electronic state lifetime interference, and double core Hall states. So let's start with the atomic Auger Doppler effect upon emission of fast photoelectrons. These are measurements we performed on the neon system. So this is the philosophy of the experiment. We published it last year. So basically, what we do, we use synchroradiation to ionize neon, the decay shell, neon 1s. So as most of you know, if this is the direction of the synchrotron beam, this is the direction of the E vector. And since the photoemission process is a dipole process, the distribution of the emitted photoelectrons is a cosine squared distribution around the E vector. So let's see if we induce this photoionization, and we produce, if the photon energy is high enough, we will produce really energetic electrons. And the electrons will be emitted basically along the vector, along these 2 cones. So they will impart a recoil kick to the neon atoms or ions left behind. So these neon ions will start moving in 2 opposite directions along the vector. In our experiment, we collect Auger electrons, and our energy analyzer is here. So basically, we will collect Auger electrons in this direction, which come from neon ions moving towards the detector, or Auger electrons, still in this direction, coming from neon ions which move in the other direction. And that will imply a Doppler shift in the energy of these Auger electrons. And if the photoelectron energy is high enough, finally, we will see a double peak in the Auger decay. So this is the experimental result. So this is a kinetic energy scale, because it's Auger, of course. And we have selected one particular final state for Auger, which is this final state here. But what I'm describing holds for the whole spectrum. So these spectra are taken as a function of increase in photoelectron energy up to about 13K electron volts, which is the maximum, the maximum we can reach. So you can clearly see that this Auger peak becomes broader and broader, and finally it splits in two components. So we have the dots are the experimental point, and the red is a simulation of Doppler effect, basically a semi-classical simulation. So you can clearly see this Doppler effect when the photoelectron energy is high enough. Now, we consider this result interesting from a fundamental point of view, but it could be also useful to derive some parameters. For instance, in this case, the angular distribution of the photoelectron is well known because it's a K-shell ionization. And also, we know the percentage of linear polarization of the synchronous light, which at galaxies is about 100%. And both these parameters are included in the simulations. Now, if instead of a well-defined system where the angular distribution is well known, like neon, we will have another system where this angular distribution parameter is not known. Let's say, for instance, argon 2p at very high photon energies. With this technique, would be possible, instead of, let's see, we go to 50 kiloelectron volts. Instead of measuring extremely high energy photoelectrons, we could measure low energy Auger electrons, and using this kind of simulation, we could derive the unknown angular distribution parameter. Or there are some new light sources where the percentage of polarization is not exactly known. It could be hard to measure. So again, if we would use a system where the angular distribution parameter is known, and we would do this kind of measurement, we could also derive the percentage of polarization in case it's not known. Next topic, electronic state lifetime interference. Now, people who work in the soft X-rays, that will remind them of the vibrational lifetime interference, which has been well described in the soft X-ray regime. So basically, in some sense, there is an analogy with this other kind of interference. And so basically, let's say we measure an absorption spectrum. And so we have some discrete states below threshold, and then we have the ionization threshold. If we measure it for a relatively shallow core level, like for instance, argon 2p, the discrete states will be well separated. If we measure it for a deeper core level, like for instance, argon 1s, the discrete state will be very broad because of the lifetime broadening, and they will overlap. So if we excite to this core excited states and we look at the decay, in this case, where they're well separated, they will decay separately. In this case, it would be possible to coherently excite more than one intermediate state at the same time. And if I can decay to the same final state, we will see interference in the decay. And the first case we have studied is argon. We have just published this paper. So let's look at the experimental results. OK, this red curve is the absorption around the K edge. So the strong transition here is the argon 1s 4p. Then we have the argon s 5p, 6p. And then here we have the ionization threshold. We measured the resonant Auger spectra. And we showed the data with what we call a 2D map. So this is a photon energy scale. This is kinetic energy scale. So basically what we do, we measure in the photon energy region of interest around the K edge many resonant Auger spectra spaced by about 100 millivolts in photon energy. And so if we report all the spectra in this kind of plot, we can immediately see what's the behavior of the final states following Auger decay. For instance, here, OK. This line corresponds to the, Any chance? Well, okay. Is this another? Okay, sorry, that's died on me. No, okay. This line here corresponds to the strongest 2p minus 2 4p final state from the decay of the argon 1s 4p resonance. This other coupling is the 2p minus 2 5p, 6p, etc. This way of presenting the data allows to see immediately what's the variation in intensity for the particular final states. So we can see that here at the argon 1s 4p, most intensity goes to the final state 2p minus 2 4p, but we have some intensity also from the 5p. Here, the 5p excitation, we see intensity from the 5p, the 4p, and the 6p, etc. Now, this is well known because we know that there could be shake-up and shake-down processes. But there is more to it in this particular example. So if we plot the cross-section for these final states here, this is the absorption curve. So for instance, here at the position of the argon 1s 4p resonance, we see that both the 2p minus 2 4p and the 2p minus 2 5p final states go through a maximum. But if you look carefully, the maximum is not in the same photon energy position, and also the shape of these curves are not symmetric, they are asymmetric. So this shift in maximum photon energy and this asymmetric shape is the signature of electronic state lifetime interference. We have here the experimental data, and the theoretical data calculations are as calculations by Brad-Arman. So this is clearly the signature of this process. We have measured another system, which is xenon. We measure the L1, L2, L3 edges. So these are the 2D maps for xenon. So the main final states are 3D minus 2, 6p, 7p for the L1, 3D minus 2, 5D, 6D for L2, and also for L3. And again, we can plot the cross sections. And we can, again, we see distortion. And also another effect that we can notice that in some case, like here, this 3D minus 2 7p final state, the cross section, the width is much narrower than the lifetime width. While, for instance, for this other final state at L3, the width is larger than the lifetime width, which means we can detect both constructive and destructive electronic state lifetime interference. Now, is this a phenomenon typical of atoms? Of course not. We have detected it also in molecules. Okay, so also in molecules, we can have different intermediate state which can decay and show interference patterns. In molecules, we can also see nuclear dynamics, but I don't have time to discuss that. So we measure, for CH3Cl and HCl, we measure the resonant Auger spectra around the chlorine K edge. So these are the absorption spectra. And you can notice that there is a difference in relative intensity for this first structure, which corresponds to the excitation from the chlorine 1s to the LUMO, and the following structures which correspond to the excitation to the Rydberg series. The Rydberg series is much more intense for HCl. And this reflects in the final states, and in particular reflects on the strength of the interference. So these are the results. Those are the cross-section for the main final state, 2p minus 2 LUMO and 2p minus 2 Rydberg. So for CH3Cl, we don't really see a shift. Maybe we see a little asymmetry, but we don't really see a shift in the position. For HCl, we clearly see the asymmetry and the different maximum at different photon energy. So this is an effect we can also measure in molecules. Okay, the last topic I would like to discuss is the direct observation of double cohorts shake-up states in photo emission. Now, Francis has already introduced the double cohorts, and he has already described the fact that they could be observed either by single photon two electron emission, and in this case, you need to do coincidence measurements to measure 2 photoelectrons and 1 or 2 Auger electrons at the same time, and that's what Francis and his collaborators do with the magnetic bottle. Or the other way to create this double cohort state is that XFEL sources, like mainly has been done at LCLS. In that case, we have sequential 2-photon absorption, and the trick there is that the light pulse should be so short that the second photoemission process should be possible before the Auger decay kicks in. And there are several examples in both of these research lines, and Francis has shown some of them. But we thought that there was a third possibility to study this double cohort. We thought that we have a highly performing beamline, which is galaxies, and we thought, why we don't just try to observe the double cohort directly in traditional photoemission. Now, of course, in photoemission, we cannot observe double cohort state, meaning state with 2 vacancies and doubly charged states, because in that case, there are 2 electrons which are emitted, and we need coincidence measurements, because the 2 electrons will share the energy. But we decided to try to measure double cohort shake-up states, which are the state that Francis called K-2V states, and to do it directly with photoemission, observing 1 electron at a time. So we had a beamline with high performances, high flux, and high resolution. So we tried single-channel measurements. And then we found that it is possible to have, the first example we studied was argon. And in argon, it's possible by just traditional photoemission, the immediate identification of state of this type, state with 2 core holes, argon 1s-1, 2p-1 NP, and argon 1s-1, 2p-1 NS. So we could make a prediction for the position of this double cohort, let's call them super shake-up states, and those were relatively easy to locate. So this is a spectrum, and so the relative intensity for these features compared to the argon 1s-1, the main line, is about 4 orders of magnitudes lower. But at galaxy, we measure the argon 1s main line, it's 1 million count per second. So really, we could afford to lose 4 orders of magnitude. And the spectrum, this kind of spectrum takes some hours to detect, not days. And so this is the theta 1s-1, 2p-1, NS, NP here. And then we have even double shake-ups, 1s-1, 2p-1, 3p-1, NP, and prime P. And then we also have the 1s-1, 2s-1 Rydberg states. So we published this recently. So let's look at a blow-up of this part of the spectrum. So this is the core, and we can identify the 3 Rydberg series leading to the 3 threshold for argon 1s-1, 2p-1, the 3 triplets, and the singlet. And we could clearly identify many Rydberg states. And so we have the experimental data and the simulations here. Now, it's possible to perform a detailed assignment of the spectrum. Also, if you look at this part of the spectrum, you can see that this is the argon s-1, 2p-1 Rydberg series. So you can just look at this part of the spectrum and think of it like the absorption spectrum for the argon 1s, not for the neutral argon, but for the argon with a 2p core hole. And what can we learn from that? We compared this portion of the spectrum with the regular argon 1s absorption spectrum. This is the comparison. Of course, for the argon s-1 absorption spectrum, we had to stretch the scale because in this case, we have 1 core hole. In this case, we have 2 core holes which repel each other. But you can clearly see that the identification of the spectral structure, the Rydberg series, is easier in our case because they are more spaced. And also, we can identify some states which in regular photo absorption are forbidden. So by measuring this spectrum, which we can consider the spectrum of the argon ion, we can also derive information on the neutral argon. So we continued this research line, and we decided to try to measure K-2 super shakeups. So we looked at neon. So that would be the double cohorts that I've seen. We cannot see because we will need coincidence measurements. And then there will be 2 steps for the Auger decay. The first step is what's called hypersatellites. But we could measure this singly charged state with 2 core holes and 1 excited electron. And we could look at the Auger decay for this particular state. And these are the equivalent of the spectator Auger decay and the participator Auger decay. So we could measure the neon hypersatellites. So these are the spectra. So those states are 1s minus 2, 3s, 3p, etc. We measured them at different photon energies because, as Francis described before, we can also, for the super shakeups, we can distinguish between direct and conjugate shakeups. So we wanted to look at the energy, the variation in relative intensity as a function of photon energy. And then we also measure the hypersatellites. So this is the Auger spectrum for the neon, the single hole. So the hypersatellites are here, but with our system, we have enough resolution, enough intensity to see them. So this is a previous literature spectrum, and this is our spectrum. And we can assign, in our spectrum, some satellites of the K-1, the satellites for the K-2, and for the K-2b. Now, final topic. Can we measure double cohorts also in molecules? Yes, we can. Otherwise, I wouldn't have asked the question. So this is CS2. We measure carbon 1s double cohort. This is the spectrum. So it's the super shakeups with 2 holes in the carbon 1s. And this is the double ionization threshold. And the spectrum has been calculated by Stéphane Carniato. Sulfur K-edge, again, sulfur 1s minus 2 satellite. We have only 1 peak here, so we don't have the calculated spectrum. And we also measure SF6 at the sulfur K-edge. Again, sulfur 1s minus 2 satellites, and this is the calculated spectrum. And the fluorine K-edge. So again, the super shakeups and the double ionization potential and the calculations. So let's say with a highly performing beamline like Galaxy, it's possible to have direct information on this double cohort states, or rather on this double shakeup states with single channel measurements. Okay, I guess this is the bulk of what I wanted to describe. I can conclude just showing the list of collaborators. So all this work has been performed at LCPMR in Paris in collaboration with Marc Simon Group. So Marc, Renaud Guillemard, Loïc Journel, Tatiana Marchenko, Oksana Trapnikova, and Gildas Goldstein. For the double cohort spectroscopy, we have a collaboration in-house, the group from LCPMR, Francis, Pascal Aublanqui, and we have a theoretical contribution from Stéphane Carniato. Again, for the double cohort story, we have a collaboration with Raymond Pfeiffer and John Eland, University of Gothenburg, and Oxford University. Last year, we had the late Dennis Lindell spending a sabbatical in Paris with us. He was working on some of these experiments, and very sadly, he passed away a few months ago. Last year, we also had another guest in sabbatical, Alex Lago from Brazil. And in our list of collaborators, there's a special place for Ralph Püttner, who's willing to, from Berlin, who's willing to join us in almost all the experiments on Galaxy. And finally, this is the Galaxy team, Denis Serlin and Jean-Pascal Rueff. Thank you for your attention.